Okay, welcome to the first video for the week on our topic, Divide and Conquer. So, Divide and Conquer is a programming or problem-solving paradigm that partitions a problem or divides our problem until it is small enough to be solved or conquered. Then our solved problems are then combined together to solve the bigger problems by combining. So yun yung three major steps ng ating divide and conquer algorithm. So divide, conquer, and then combine. So makikita niyo yun dito sa figure natin here below. So we started the problem, i-divide natin sila, pwede pang i-divide ulit, and then i-conquer yung mga maliliit na sub-problems. And then i-combine para ma-solve yung sub-problem. And eventually, masasolve na natin yung big problem natin. So, yung sinasabi dito, recursion is particularly useful for divide and conquer since we can divide our problem recursively until we reach a base case. So, kung ano si problem, para i-solve siya, di-divide natin siya and apply the same algorithm sa sub-problem. So, yung sub-problem is mo divide and then so on and so forth. So I guess you can best see this with an example. So for our first example, this is what we call searching or paghahanap. For example, meron tayong list ng student numbers of students enrolled in EEE 121. Kung ano 10 lang kasi hindi kasya sa screen yung madami. So, ayan. So, ang goal natin is to find the particular index of a student. So, hanapin yung index 6769, which is index 4. And then return -1 is if the student is not in the list. So, this could be important kasi di ba hindi naman lahat ng student numbers nag-exist. So, para malaman kung pang ilang student ka talaga, kahit yung depending on your student number, we will use itong searching na function na to. So, yung straightforward na approach is isa-isayin natin lahat ng elements doon sa list. So, starting from the first index, I equals 0, and then while I is less than n, basically, isa-isayin lang natin yung elements din sa list hanggang makita natin siya. So if yung SN list I nag-equal dun sa key na nilagay natin dun sa argument ng function, i-return na lang yung index na yun. Then if hindi pa siya equal, dun siya sa next na index. Eventually, hanggang dun sa dulo, if ma-reading niya na yung dulo ng list at hindi niya pa nahanap yung item, it will return -1. So pwede nyo i-run to if you are using yung ating OLAB notebook. So yun, 9932 is nasa dulo, so index 9. And then for example, palitan natin 8184. Pag run natin yung code, we get yung index niya which is 5 kasi siya yung 0, 1, 2, 3, 4, 5th element. And then if we add if we look for something na wala dun sa list, for example, 1,500, it should return -1. So, looking at the complexity of the algorithm, ang worst case natin, hopefully obvious sa inyo na, ang worst case natin is linear time complexity, wherein dumaan tayo sa lahat ng elements ng list and hindi natin makita. So, linear siya kasi pag nagdoble yung list natin, dodoble yung number of iterations ng ating loop. Then for the space complexity, since yun nga, iterative function siya, wala naman tayong ginamit na extra na lists or malalaking containers or variables, our extra space or auxiliary space complexity is just constant or 1. So, paano tayo makakakuha ng implementation na mas mabilis sa linear? So actually, ang linear na time complexity nga, if napansin nyo sa previous lectures, it's actually pretty fast already. Pero pwede pa natin siyang pabilisin. And that is with the CHAD approach called time search. So we can take advantage with our list na sorted siya. Meaning, yung pinakamaliit na student number, siya ay nasa index 0, and yung pinakamalaki is nasa index 9. So, pwede natin gawin, pwede natin i-divide yung ating input. Given yung ating key, we can find the middle element or middle index by getting n equals 2. So, n is yung length ng ating list. And then, i-compare natin if the if the element we're looking for is greater than or less than dun sa ating list. So, for example, dito yung key is 9932. Expect annotate. So, if yung key is equal to 9932, we can check our middle element. So, I think it would be this guy. So, i-compare natin. So, yung hinahanap natin is much greater than. So, ang consider na lang natin na list is this one. So, kahit hindi na natin pansinin nandito. So, we can do that because we know na sorted yung list. So, si 9932, mas malaki siya dun sa middle element. So, nandun dapat siya sa upper half ng ating list. So, yun yung nangyari dito. So, si key, mas malaki siya kay list, ay yung middle of the list. So, yung starting point ng loop natin kanina, dito, is yung middle point na. So, hindi na natin kailangan tingnan yung first half ng elements. Pero, pag ginawa natin to, let me just do yung drawings. Ang ating worst case time complexity is magiging big O of n over 2, which is the same as big O of n. So, linear pa rin siya. But we just made one partition. So, what if take natin siya one step further and i-divide pa natin siya ulit dun sa next one. So, after dividing it by half, so after tanggalin ng first half, we consider yung second list and we check ulit yung middle element and then we remove yung half na hindi pa natin or hindi natin kailangan check. So, for example, kung 9932 yung nahanap natin, if we compare it sa middle element, mas malaki siya. So, we no longer have to check yung first half ng element. So, we are left with two elements na lang. And then, yun. So, makikita nyo dapat na si 9932 nandito. So, makikita nyo pa lang dito, we no longer have to check 1, 2, 3, 4, 5, 6 elements. So, parang ang chinek lang natin is yung middle elements ng kada partition. So, by that observation, we can expect na medyo mas mabilis dapat yung approach natin na to. So, let's just put that in a more defined na function. So, yun nga, so it will utilize recursion kasi we can skip muna to. So, right here, we get the middle element and then we compare the key to the middle element. If mas malaki siya, we apply binary search doon sa upper half. Otherwise, if mas maliit, we apply binary search doon sa lower half. And then if nag-equal, we actually found the element. So that is a fortunate case. And then yung base case natin dito for the recursion is when our list or the sorting list only has one element left. So if isang element na lang, kailangan nyo na lang check if yun yung element na hinahanap mo or hindi. Otherwise, naubos mo na yung list and hindi mo nahanap yung item. So notice here how we utilize yung recursion to solve our to form our solution. So yung initial list, hinati natin. So in order to search for the element in our whole list, we divide our list into two. So, and then we notice kung alin half yung kailangan natin i-observe. And then, actually, yung one list kaya natin i-eliminate. And then, paano natin nahanapin yung element sa remaining part ng list? So, we apply the same algorithm. So, we apply binary search to this sub-array, wherein, yun nga, hahatiin mo ulit yung elements, and then search for the key dun sa remaining elements. So, and then paano mo hanapin doon? We use binary search again. So, parang Since our divided problem is a smaller version ng original problem, we can use the same function. And yun nga, particularly useful din yung ating uh, recursion. So yun, since we use recursion, if we want to examine yung kanyang time complexity, we need to look at the recurrent solution niya. So yung time complexity ng initial call, so T of n, is equal doon sa pag-call sa kanya ulit, but n is half now. So starting from 10 elements, may 5 elements. After yung 5 elements, may 2 elements. So after each recursive call is nahati yung ating list natin titignan. So yun, every other command or every other operation naman sa ating function ay constant yung kanyang time complexity, so plus C1. And then pagka base case is C, another constant. Then, so using the substitution method to get yung closed form expression with T of n, ayun, so mag-start tayo with the recursive call over here. And then expand lang siya. So the more we expand is lumiliit yung nandito sa loob ng T of n na term, pero yung C term natin, yung constant term natin is dumadagdag by 1. So kada hati dumadagdag yung ating coefficient. So we can substitute an expression for T of n, or we can use k, 2 to the k actually, to represent yung divisor. And then k i-multiply sa c. So we can apply, kunwari, k equals 0, we get, or actually k equals 1, we get yung first term here. So for example, if k equals 1, we get yung n over 2 plus 1 c2. But if we use k equals 2, we get naman na over 4 and plus 2 c1. So yun, medyo mukhang tama naman siya. We can use other methods to prove na totoo siya. But, ayun, assuming na tama siya. Ayun, kailangan lang natin kailangan lang natin i-force na yung nasa loob ng parenthesis natin or yung sa T of n na term is equal to 1. So that is when n is equal to 2 to the k, which gives us k as log base 2 of n. So plugging that into our original expression, so ang nangyari, si 2 to the k, naging n, kaya naging n over n siya over here. And then si k dito is naging log 2 of n, kaya naging c1 log n. Then simplifying further, si t of n over n, this is equal to t of 1, which is yun nga, based sa ating original na representation. Pag t of 1, or when n equals 1, ang t of n natin is c2. So may c2 lang siya over here, and then c1 log n. And then getting yung asymptotic or yung big O, yeah, we get that big O nitong expression na to is just log of n. So we can confirm na yung binary search natin is better than linear search in terms of running time. But however, kailangan din natin consider, since recursive function siya, it uses additional space. So to get the auxiliary space complexity, first visualize yung ating recursion tree, which doesn't really look like a tree kasi starting with the whole of the list, tapos half of the list, a fourth of the list, etc. etc. So ang kailangan lang natin makuha actually yung ating depth, or ayun, essentially yung partition natin paliit siya ng paliit. So initially starting with n, naging n over 2, n over 4, and eventually making n over 2 to the level. And if you want to get to the depth, ibig sabihin nun, n is divided by 2 to the n. Kasi magsa-stop tayo pagka yung partition natin is approximately 1. So if yung partition natin approximately 1, we can get yung ating depth ng recursion, which is log of n. So yun also yung space naman natin. is log of n times a constant. Since all of the functions naman, wala naman tayong ginagamit na extra list. So we're just using the same list over and over again. Nag-iiba lang yung parang limits ng ating expression dito or yung arguments natin. So without using an additional list, ating auxiliary space complexity is log of n or logarithmic. So which means na pag nag-double yung ating space or nag-double yung ating array, yung pag-increase ng kanyang time is not hindi siya magdo-double by itself. So parang pag nag-double ka 4 times, mag-plus 2 yung auxiliary space na ginagamit. So hindi siya linear na relationship. Which is relatively okay, lalo na if yung system mo naman is not uh, limited in terms of memory. So it's a small price to pay for the faster and better na running time. So yung ating verdict over here. So is binary search better than linear search? So the answer will depend on which resource you're willing to give up. So binary search uses a bit more memory but faster than linear search. And then ayun nga, if okay lang sa'yo maghintay, pero wala kang memory, so okay lang na gamitin yung linear search. And then actually, yung trade-off na to between yung ating running time and yung memory or auxiliary space is a recurring trade-off in our future algorithms, lalo na dito sa divide and conquer. So, pwede ba natin implement yung binary search without recursion? Actually, that is possible. And it might be even better in terms of memory. So, baka magkaroon pa tayo ng action. Ultimately better. So, without sacrificing in additional space, we can come up with a binary search na hindi gumagamit ng additional memory. So, ginamit na natin yung recursive implementation dito because it is more applicable or much more similar din sa ating future algorithms na i-represent for divide and conquer. And that will be covered in the next video. So thank you very much.